Good morning, students. In the last class we have discussed the dynamic consideration. And we have discussed what is the introduction, why we have to consider the dynamic, and what all the things are there in the dynamic, and consistent mass matrix and lumped mass matrix. Okay, so today we are going to start a problem, a bar problem considering dynamic analysis. Okay, so here for the stepped bar shown in figure, determine the eigenvalues and eigenvectors. Take area is A1 stepped bar of A1. Stepped bar A1 is 400 mm square, A2 is 200 mm square, and density of the stepped bar, density of the material, rho is equal to 7850 kg per meter cubed. So now in this case, dynamic thing, we are considering the mass. So Young's modulus is 200 gigapascal. So here I have put it all in meters because my rho, mass density rho, is in 7850 kg per meter cube. The density rho should always, the unit should be kg per meter cube. Don't convert this into Newton per meter cube. Let it be kg per meter cube. Okay, but meter I have, so I am converting all the values in meters. So this becomes Young's modulus 200 10 raised to 9 Newton per meter square. This is 4 into 10 raised to minus 4 meter square, and 2 into 10 raised to minus 4 meter square. Young's modulus. Length here is given 200, so 200 mm is 0.2 meter and 0.1 meter. So very first step what we have to do here is what? So FE model. Now I am creating the FE model. See, consider here in the dynamic analysis we are not putting any force here, so we are considering the mass. Means what? How it behaves, how the behavior, and what are the eigenvalues and eigenvectors. So I said you why we require eigenvalues and eigenvectors. So eigenvalues and eigenvectors gives us the frequency of the particular material or frequency of the particular component. Once you know what is this frequency, we can easily identify when the component is in load, when the component has an impact load or dynamic loads, then it is easy for our calculation. Okay, start with the problem solution. First, FE model. So FE model, I have two elements, 3 nodes, stiffness matrix and mass matrix of the element. So here the stiffness of matrix of the bar remains same, and the mass matrix. Okay, so we need to consider mass matrix. So in the last class we have discussed 2 mass matrices. One is lumped mass matrix and consistent mass matrix, but our problem we should go with consistent mass matrix because consistent mass matrix gives you accurate results compared to the lumped mass matrix. But when you have a complicated structures like big structures where you have a n number of parameters are there, then we are going for lumped matrix. So this is very simple problem, so I am going for consistent mass matrix. So stiffness of the bar element remains same here. K1 is equal to A1 E by L1, 1 minus 1 minus 1 1. So area A1 is 4 into 10 raised to minus 4, 200 10 raised to 9. Length L1 is 0.2, and if I substitute, I got K1 is equal to 10 raised to 8, 4 minus 4 minus 4 and 4. Okay, next. So the mass matrix. So the mass matrix M is equal to consistent mass matrix for the bar element rho A1 L1 by 6. This actually we have derived how we got this mass matrix. So M is equal to rho A1 L1 by 6 2 1 1 2. If I substitute the rho 7850, be careful, the rho always it should be kg per meter cube. Okay, it should be kg per meter cube, and all the values of length, area and Young's modulus keep it in meters. Okay, 7850 into 4 into 10 raised to minus 4. L1 is 0.6 divided by 6. I got the matrix 209.34. Sorry, 104.67 10 raised to 3 minus 3 I got. When I multiply with the 2, I got the double value here diagonally, and this value remains same here. So I took a common of 10 raised to minus 3. So okay, now stiffness matrix and mass matrix for the element 2. So here 2 elements have there. For the first element we have derived the stiffness K1 and M1. Now we will derive K2. So K2 is 2 into 10 raised to minus 4 area into Young's modulus 2 into 10 raised to 9. Length is 0.1. Here also I got the same value. Same for the stiffness matrix. Here the values are different, but the values for A1, E1, A1, L1 and A2, L2 are different, but even though I got the K1 value and K2 value as same. Okay. Next, mass matrix for the second element. Here rho, area and length is going to change. 2 into 10 raised to minus 4, 0.9. So here I got 26.17 into 10 raised to minus 3. When I multiply with 2, it is doubled, 52.34 diagonally, and 26.17 diagonally here. Okay, this is a mass matrix. Now the global stiffness matrix of the stiffness matrix and mass matrix. So I said you the global stiffness matrix already we have discussed here. So here this is 1, 2, 1, 2, 1, 2. Okay. So for this is 2, 3, 2, 3. Okay, Baba. So globally what I will get 1, 2, 3, 1, 2 and 3. When I compare the 2, 2, so here I have a 2, 2, remaining things values remains as it is here. So 2, 2. So here 2, 2 is 4 and here 2, 2 is 4. So what happens? I will get a 8 here. Okay. So remaining values remain same. 4 minus 4 minus 4. This is 4 plus 4 minus 4 minus 4, 4. Remaining thing becomes 0. Okay. So okay, same way for the mass matrices. So for the mass matrix also, node 1, node 2, node 1, node 2. Here node 1, node 2, node 1, node 2. So this is 1, 2, 3, 1, 2 and 3. Fine, Papa. Same thing, the mid of this element is going to add, where 2, 2 I have. So here in this case, this value, and in the previous case this value, sorry, not this value. So in this case this value and here this value is going to add, means upper triangular matrix 209.34, 104.67, 104.67 remains as it is here, and here in this case lower triangle remains same here. This lower triangle remains same. Only the diagonal part in the middle is going to add this value, and remaining things becomes 0. Fine, Baba? Okay. Fine. So this is what global stiffness matrix and global mass matrix. Okay. Now we have to find. So now we have found stiffness matrix and mass matrix. The eigenvalue problem is given by. So I said you in the DOM you have discussed already m x double dot plus kx is equal to 0. This is a mass acceleration equation, or we call it as a motion equation. From this equation this is derived. K minus lambda x is equal to 0. Okay. So k minus lambda x is equal to 0. So from the mass matrix it is derived. Okay. Fine. So here this equation we got directly, k minus lambda x is equal to 0, where k is the stiffness matrix, m is the mass matrix, lambda is the constant, or lambda is called eigenvalues. So where we need to find that eigenvalues using lambda, and also from the lambda we can find the frequencies also. Fine. Okay. So where x is what? Displacement. Q1, Q2, Q3. So we know the global stiffness matrix K, 10 raised to 8, 4, minus 4, 0, minus 4, 8, minus 4, 0, minus 4, 4, minus 10 raised to 3, lambda, and mass matrix remains as it is, what we have derived for the global mass matrix here. This total mass, global mass matrix comes here, there, global matrix comes here, and x is what? Displacement, Q1, Q2, Q3, where x is equal to Q1, Q2, Q3. This is called a global displacement vector. Okay, fine. So now applying the boundary conditions at node 1 is fixed. Okay, so why node 1 is fixed? So from the given data, the node 1 at the starting bar, so it is fixed. So at node 1 it is fixed. So eliminating first row and first column. So if I eliminate first row and first column of the total equilibrium equation, even in the mass matrix and stiffness matrix, I left with 8 minus 4 and 261.67, 26.17, 26.17, 52.34. Fine. So this is what I got here. So now I have eliminated. After elimination, I got this equation. Now how to solve this equation? So to find eigenvalues, the characteristic equation is, so this is a mathematical equation. To find the eigenvalues, we need to know the determinant of the known matrix. So here I have the known matrix where K minus lambda m. This is a known matrix. So for this, if I make a determinant is equal to 0, I can find the eigenvalues. Okay. So now what is the determinant here? K. So this is the determinant symbol. So I need to put a vertical line there. Okay. So I need to put a vertical line here. So vertical line where K is what? 10 raised to 8. 8 minus 4. 4 and minus 10 raised to minus 3, this remains same. Determinant is equal to 0. Now how to add these two things? So here before I multiply, here the total matrices, there is an addition here. So subtraction I have. First I need to convert this. So here 8 into 10 raised to 8 minus 261.67 into 10 raised to minus 3 lambda. So this comes 1 comma 1 and 1 comma 2 4 minus 4 into 10 raised to 8 minus 26.17 into 10 raised to 3 lambda. So this comes. So first I am going to add this regular matrix addition, this later this and this and this. Okay, so 1 2 2 3 and this is 4, this is 4. Okay, so after addition what I got here is what? So after addition I got this values. So now I got the determinant matrices. So this is 1, this is 1, this is 1, this is 1. Now 2 by 2 determinant matrix I got. Now I need to multiply these two values here. Now how to multiply here? First you have to multiply from the left top corner to the bottom right corner. This is 1. I have already specified this symbol there. Already I specified the symbol there. So left corner to right corner. So total this value into this value. So how to multiply this? 8 into 10 raised to 8 into this 8 into 10 raised to 8 minus of this. Again these two values and this two. Same way here. Here you can observe carefully 4 minus 4 into 10 raised to minus 8 minus 26.167 into 10 raised to 3 and this thing, this value. Both are same. I will square it. So in the next slide, can you see here? Both are square here. So both are square. So here 8 into 10 raised to 8 minus 26.67 into 10 raised to minus 3 into 4 into 10 raised to 8 minus 52.33 into 10 raised to minus 3. So here after multiplication. Okay. Okay, these two multiplication. Okay, after this multiplication, so here I wrote this total value into this total value. Here I am going to multiply 8 into 10 raised to 8 into 4 into 10 raised to 8. 8 into 10 raised to 8 into 4 into 10 raised to 8. And 8 into 10 raised to 8 into 52 point this thing. Later minus 26.674 into 4 into 10 raised to 8 Next, minus 26.67 into 52.34 into this value. So this. So here I got the total whole square. So I can write a plus b whole square formula here. A square plus b square plus 2a into b. So now here I am going to make little bit arrangement here. So when I may multiply this, I got the value 3.2 into 10 raised to 9. Okay, 3.2 into 10 raised to 9. One second. So these two, after these two multiplication I got this value, after this multiplication I got this, after these two multiplication I got this, after this multiplication I got square I got here. So here I got the constant value, here also square value I got, and here I got lambda. Now I am going to separate the square, lambdas and constant. So here I put a red line here. Red line here, this is a total lambda value, this is this two lambda value and this lambda value. I am going to add this and this. Okay, so I have a calculator here. So here this value. So first let me go for lambda square. So this and this both are lambda square values. So this 0.0137 minus 6.847 into 10 raised to minus 4 is equal to, I got this value 0.013053 lambda square. Okay, now I am going to add all these lambdas. So what are the lambda? First minus 41.867 into 10 raised to 6 minus 104.67 into 10 raised to 6. Okay, so this and this value minus 20.933 into 10 raised to 6 is equal to, so I got this value here minus 167 into 10 raised to 6. So here 3 and 3. So here I got a point, total 6 points, 167.470 into 10 raised to 6 lambda minus constant value remains same, 1.6 into 10 raised to 17 is equal to 0. Now how to find this equation using calculator? So when you go to the mode, in the mode equations, in the equations you have a two unknown equations and you have degrees. I need to go for degrees here. So how many degrees I have? 2 degrees. So how to go first? I should go for mode. In the mode, equation 1. In the equation I have unknowns and degrees. So go for degrees. So in the degrees I have 2 degrees. So 2 degrees. So what is A1 value? 0.01305.153. A B value minus 167.4702. Constant minus 1.6 into 10 raised to 17. 17. So I got lambda 1. One second, somewhere I made a mistake. One second. Equation 1, degrees is 2. 0.0130153. You should be very careful when you are typing this. Once or twice you have to check it, because you may, if one number is going to mix, point is going to mix, change, the value is going to change here. This is A1, B, so this is square, this is lambda. Next lambda is minus 167.4702 into 10 raised to 6, I think so, I forgot this, 10 raised to 6 is equal to, now this minus 1.6 into 10 raised to 17. Okay, now I got 1.376 into 10 raised to 10 and minus 8.9 into 93 into 10 raised to 8. If you come from back, you will get this point here, 8. So 10 raised to 8 you are going to get. So now I got the lambda 1 and lambda 2. Now I got the eigen values. Okay, now I got what? Eigen values I got, lambda 1 and lambda 2. So if you want to find the frequency, so lambda is equal to omega square, where omega square is equal to 2 pi f. F is the frequency. Fine. So once I know what is lambda, I can know omega. Once I know omega, I can know the frequency. Fine. So this is how you need to find the frequency. But in our given data is set to find eigen values and eigen vectors. Okay. So now I have found the eigen values lambda 1 and lambda 2. Now I am going to find the eigen value, eigen vector. Eigenvectors. So eigenvectors, to find eigenvectors I need an eigenvalue, but I have two eigenvalues, lambda 1 and lambda 2. So case 1, I will consider case 1. First I will consider lambda 1 is equal to 1.37 to 10 raised to 10. So here this equations comes here. So here we have this equation, isn't it? So to find the eigenvector, so we need to consider this matrices. Okay. So this is what this k into lambda, k minus lambda 1 m into x1. What is x1 here? q2 q1. Why I have wrote x1 is it is a case 1. For the lambda 1 I have considered na. For the lambda 1, so I wrote x1. Okay. Means what? x1 means what? For x1 q2 q3 you will get. For x2 means lambda 2 q3 q2 q3 value you will get. Means for every eigen value what are the eigen vectors I am going to get here. So now if I consider this, so substituting lambda 1 in this equation, so what happens here? So now after this, so here in this equation the lambda 1 value I am going to substitute. Once I substitute, I will multiply this lambda value in each matrix, and then I am going to add these two values, regular matrix addition. So once I do that, I got the final matrix here. You do that. So final matrix I am good. If you need, I will do it. Okay, but it takes time. So you do it. It's very easy. It's very easy. It's very easy. Okay. Okay. So once you know lambda 1 value here. So lambda 1 in each all of the matrices you multiply it, and later you add this and this and this. So you get 2 by 2 matrices. Okay. So this is what 2 by 2 matrix I got. Now also we consider. Now let me consider only one equation. This equation I can't solve using a calculator. Why? Because I don't have a constants here. It is 0. So if these values are 0, I can't find the solution using calculator. Now I need to make few assumptions to solve q2 and q3. What are that q2 and q3? Eigen vectors. Okay. So now I will consider the first equation, minus 2.8 into 10 raised to 9 q2 minus 0.7 into 10 raised to 9 q3 is equal to 0. Okay. Now if I make simple substitution, minus 10 raised to minus 10 raised to 9, if I take common and if I put divided, if I eliminate minus 10 raised to 9 here, so minus if I take common, minus 10 raised to 9 if I take common both the cases, I will this value it is divided by 0. So then left with 2.8 into q2 plus 0.76 into q3. Okay. Now even now I don't know what is q2 and q3. Let q2 is equal to 1. So this is the assumption. So how to find q2? Whether q2 is 1 itself? No. q2 again we can get the solution using normalization method. This you have already studied in mathematics, that is I think so M3 or M4 you have studied the eigenvectors and eigenvalues. So where there we are going to find the eigenvector. For the first, let's consider q2 is equal to 1. So if I consider q2 is equal to 1, 2.8 into 1 plus 0.76 into q3 is equal to 0. So here if I take q2 as 1, so what I will get here? 2.8. So this 2.8 I will take it on the other side, it becomes minus 2.8. Minus 2.8 into q1. q1 is 1 divided by what? This 0.76. How much I got the q3 value? Minus 3.76. 3.684. Now I got the Q2 and Q3 values. Thus x1, what is that x1? Eigenvector is equal to Q2, because Q2 is I don't know. Q2 is equal to Q2 minus 3.864. But if Q2 is equal to 1, when Q2 is equal to 1, I got this value. Now normalizing. Now for a normalization we get for this. So now why we are doing this normalization? I need the Q2 value, because Q2 I have considered as 1. So normalizing x1 dash, x1 transpose mass x1 is equal to 0 means the x value, the Q2 Q3 transpose and Q2 Q3 with mass, it should be always equal to 1. Based on this condition I can easily find what? Q2. So here x dash is what? X dash is equal to x1 is equal to Q2 minus 3.684 Q2. So here what I have done, Q3 I have put it in terms of Q2. How to put this Q3 in terms of Q2 here? So here I have a Q2 value here. Q2 is equal to 0.76 divided by 2.8. Sorry, Q3 is equal to same thing I will get, minus 3.684 Q2, means if I substitute this value in Q3, sorry, okay, if I take if Q2 is equal to 1, I got Q3 is equal to this thing, okay Papa? Okay, now x1 is equal to Q2, Q3 value I will put it in terms of Q2, that is what? This value, okay, fine. So now I know what is x1. X1 transpose is horizontal. So here x1 is vertical. So mass matrix what we have got in the beginning, the global mass matrix. So global mass matrix I got this, the same global mass matrix I put it here. Okay, it's the same global mass matrix. I took 10 raised to minus 3 inside here. Okay, now comes the question here, how to multiply these three values. Okay, so how to multiply these three values? So why we are doing this normalization is to find the Q2 value, because Q2 I took an assumption it is equal to 1. Okay, so to find Q2, once I find Q2 I will get Q2 and Q3. Okay, fine. So now how to multiply these three? So here how to multiply this? So here I have 1 by 2 matrix. What is 1 by 2? 1 row, 2 columns. So this is 2 by 2 matrix, 2 row, 2 columns. This is 2 by 1 matrix, 2 row, 1 column. Okay, so this is how the matrix are set. So now how to multiply? First we shall multiply these two, 1 into 2, 2 into 2. So when I multiply these two, I can easily say what is the final matrix. So 1, 2, 1 into 2 and 2 into 2 I am multiplying. When I multiply these two, always these two numbers should be same. If these two numbers are same, I can multiply the matrix. If these two numbers are not same, I can't multiply. So finally what I get? I get 1 cross 2 matrix, means 1 row 2 column matrix I will get. Okay Baba, 1 row 2 column matrix I will get. So now how to solve this? So 1 into 0.26, 1 into 0.267, 1 into 0.26167, 1 into this and this into this, minus 3.684 into 0.026167 is equal to, I got how much? I got 0.16527. I got 0.16527. Let me write it here. I got 0.16527. Okay. Okay. Now again what? This with this. 1 into this value 0.026167 into minus 3.684 into this value 0.052334. So how much I got? Minus 0.1666314. Okay, so I got minus 0.16663. So now I got what matrix? 1 by 2 matrix after multiplication of these two. So now I am going to multiply what? 1 into 2 and 2 into 1. So what I will get? 1 into 2 and 2 into 1. So these two numbers are same. I can multiply. I will get 1 by 1 matrix. Means I will get only one number. Now I am going to multiply these two. So now how to multiply those two again here? So this 0.167 into this one value, again this minus, here minus of minus, it becomes plus. So plus 0.1336314 into this value 3.684 is equal to, I got what here? Okay, 0.777914. Can you see here? I got 0.7914. So after multiplying these three matrix, I got only one value, that is what? Q2 square. So here I took a Q2 square common here. Q2 square is what? 0.77141 is equal to 1. Q2 is equal to square root of this. I got Q2 is equal to 1.1329. Fine, Papa. Now once I got Q2, so I can substitute the value in this Q2 value. Here I got directly this value 1.134129, and here if I multiply minus 3.684 into 1.1329, I'll get minus 4.17. Now I got the eigenvector x1. So using lambda 1. So lambda 1. So for the case 1 lambda value, eigenvalue, I got the eigenvector. In the second case what? Lambda 2. The same thing, the same procedure we need to follow here. So same procedure we need to follow here. Same lambda 1, lambda 2 is equal to 0. Same thing k m, k minus lambda m, q2 q3. Here directly I wrote the equation, because here this directly I wrote the equation here. So this you multiply with k minus lambda m. But in this case what? Lambda I know, lambda is lambda 2 value, I know this. So multiply lambda 2 with mass matrices, where this is the matrices after elimination. So I'll get 2 by 2 matrices, what I have in the earlier case. So in this matrices, so this is the matrix where you need to multiply that lambda 2 value. So here if I multiply this lambda 2 value inside, and if I add, so finally I'll get what? This thing. Okay, so finally I got this thing. So q2 equal to q3. Consider now again same thing. So I will multiply this. So you have to consider, you have to consider only this q1 1.037 into q2 minus 0.3766 into q3 is equal to 0. Same thing, q1 I will consider it as q2 I will consider it as 1 when I will get q3 value. So here x1 is what? q1 q2. Sorry, x1 is what? q2 q3. q3 q2 I will place it as it is here. q3 I will put it in terms of q2. So if I substitute this, you need not substitute anything. Don't consider this directly here. q3 is equal to how much? In terms of q2 you will get. That is the value here, 2.744868 Q2. Okay, fine, Baba. So here I got Q3 value by considering Q2 equal to 1. Okay, later Q2 I will place it as it is in this equation, only in this equation. In this directly Q3 value in terms of Q2 you put it here. Okay, fine. Next, normalizing X transpose mx1 is equal to 1. So same multiplication what I have explained in the previous thing, same thing multiplication you go do, I will get Q2 value, again same thing. So finally I got lambda eigenvectors. Okay, thank you, Baba. So this is how I got the eigenvalues and eigenvector. So first, simplifying the mass vector global mass matrix. By this I found what eigen values using characteristic equation. Lambda 1, lambda 2 I got. Now to find the eigenvector lambda 1 for the case 1 lambda 1. So you need to consider the same this thing and then you have to solve. Okay, thank you. In the next class we shall discuss the another problem. Okay, fine.